This time, I chose a paper entitled Using Machine Learning on Home Healthcare Assessment to Predict Fall Risk, which was published in 2019. The reason why I chose this paper is that fall is very common in older population, and the burden of fall and fall-related injuries are very enormous in aging societies. And recently, risk factors for falls are reported not only physical but also psychosocial aspects. And many previous systematic review reported that physical functions such as frailty or muscle weakness are identified as risk factors for fall. And recent observational studies added new evidence that psychosocial factors are also associated with risk of falls, such as fear of fall or self-efficacy of falls. These new evidence suggests that there will be still unknown psychosocial factors associated with fall, and machine learning will be helpful to explore new suggesting factors. And this study conduct predictive models for falls using medical claim data in the United States. In the United States, the Mohawk 10 scale is used to assess fall risk for in-hospital patients who use home health cares. The Mohawk 10 scale consists of these 10 items, including age, prior history of falls, incontinence, visual impairment, and so on. But its specificity is reported to be very poor as 0.13. This poor specificity indicates that fall positives are very common. So the purpose of this paper was to explore risk for fall among home care users in the United States using medical claim data. This study was an observational cohort study using Medicare and Medicaid data in New York City with over 100 items evaluating a patient's clinical, behavior, cognitive, and environmental conditions. Patients with age 65 years and older and both the risk for full assessment and medical claim data are available were eligible in this study. The onset of falls identified by claim data was used as an outcome, and 114 clinical and demographic variables from claim data, which is derived from OSSC data set, and the Mahak 10 items, which is scale for full risk assessment, were used as candidate features. In other words, candidate predictors. This slide shows the machine learning pipeline. They use the relief algorithm for their feature selection. The relief algorithm works by randomly sampling an instance and locating its nearest neighbor from the same and opposite class. The value of the features of the nearest neighbors are compared to the sampled instance and used to update the relevance scores for each feature. In my understanding, the relief algorithm is like propensity score matching. They applied five-fold cross-validation in which the whole data were randomly split into 50% of training data and the 50% of testing data. This split procedure is so-called outer split. Then the training data is further split into 10% of the remaining 40% was used as validation dataset. This training procedure is repeated 5 times, so that's why this method is called five-fold cross-validation. In this procedure, hyperparameter optimizations were performed, and then final evaluation is performed using this test dataset to calculate precision recall curves, AUC, and ranking the features. They applied random forest classifier for learning algorithm, and they conducted several models as shown here. First, only the clinical and demographic data, which is derived from OSSC dataset, and then full related only dataset, which is derived from each Mahak item, not aggregated one. And third, combined with both the OASIS and each Mahak item. And finally, full assessment score, which is derived from Mahak 10 score, which is aggregated one, as reference. This slide shows the main result of their study. They reported that OSS model and the combined model had almost identical metrics that outperform the full related data. As shown this here, however, the value of the AUC in combined and OSS data were 0.67 and 0.62 respectively. The value for the AUC for best model is reported to be more than 0.8, so both the combined and the OSS model are not predictive models. They also reported the feature importance, which is generated from the random forest classifier. They reported age as the most important feature to predict fall, followed by average and total severity of home care diagnosis, frequency of therapist visit, and pain. They also reported the correlation between full related features and the clinical and demographic data features to discuss why the accuracy was not dramatically improved. As shown in this figure, they reported that all Mahak items were correlated to one or more OSS items. Let's think why the prediction of accuracy did not dramatically improve in this study. They reported that higher precision and balanced accuracy were observed in combined data than the commonly used multifactorial Mahak full risk assessment. They also reported that all Mahak items were correlated to one or more OSS items, complementing the OSS features with the 10 Mahak items did not result in detectable improvement over the OSS only model. So, the reason why the accuracy did not dramatically improve in this study might be a lack of psychosocial factors that might be important for older people to predict fall. From machine learning perspectives, They applied random forest algorithm for feature selection, but it would be better to use Boruta algorithm, which is based on random forest classifier for precise feature selections. They applied fivefold cross-validation, but would be better to use nested k-fold cross-validation for less biased model evaluations. This slide showed the outline of the nested k-fold cross-validation. As shown in the upper figure, this is the same as the k-fold cross-validation procedure. But in the nested k-fold cross-validation procedure, the training procedure is performed using the previous testing dataset, and then the training procedure is performed using the previous training dataset. So that's why this method is called nested k-fold cross-validation. But for more precision, repetition of the procedure can be implemented. So repeated nested k-fold cross-validation would be better for more precise model prediction. They applied random forest classifier for the learning algorithm, but would be better to use gradient boosting method for better accuracy scores. This slide shows the difference between gradient boosting and random forest classifiers. As shown in the left side of the figure, the gradient boosting method is like a serial learning, which builds trees one at a time, where each new tree helps to correct errors made by previously trained tree. On the other hand, as shown in the right side of the figure, random forest classifier is like a parallel learning, which trains each tree independently using a random sample of the data. And it has been reported that gradient boosting trees performs better than random forest if careful hyperparameter optimizations were applied. So far, applying gradient boosting would be better than random forest algorithm to conduct predictive models. Thank you very much.